The saga continues. When I last left you, I believe the code was getting rather complex and I was struggling to manage to make good updates in a short amount of time. So what I decided to do was off camera, I went out, I refactored the code to making it nice and generic. Any number of pivots, can go into any number of bins for the sort, and it's just looked very nice and clean and tidy, and it was slow as a dog, which is kind of what you expect when you make things very generic. And so then from that point, I decided to split into two different tracks. So I would do one for the quick sort style, just using 2 bins, and another one in a sample sort or radix sort one with a fixed number of bins, 8 bins. I think last time we were looking at doing it 4. And then basically undo all of the generic code I'd done and sort of re-optimize. What I encountered was I wanted to be able to do more simmed operations. In particular, I wanted to do some parallel less thans. And you can't do them in 64-bit integers without AVX 512. So you can either add heaps of operations to do bit twiddling and permutations and stuff, or what I did was just shift the goalposts and start sorting 32-bit integers instead. So now the problem scope has changed. And with that, I was able to make some modest improvements. I haven't done a lot of it. I guess we can do some more today. But the competition has also improved. It's able to sort 32-bit integers, and let me show you what happened. Over here, my quick sort is now the blue one, and the sample sort is red. Pretty slow. In fact, they're even slower than the... not pretty slow. They're all right. But they're slower than the PDQ sort. This is nanoseconds per operation, so they're slowly getting less efficient as the array size gets larger. But that's okay. They're not fully optimized. However, what I wanted to point out was this orange one. I think last time I said it was the radix sort. That was wrong. This is the quick sort, the simmed implementation of quick sort that is in the NumPy. And it is incredibly fast. So I guess that moving to the 32-bit integers mean that it can suddenly use a lot more of its simmed operations than it could before. In fact, let me show you what it's doing. Is here. This is NumPy's x86 simmed sort. It's written in C, I think, or maybe C++. C++. If we go to source, you will see it comes with a bunch of different fixed implementations for every size. So I guess we're in competition with 32-bit qsort. And it looks stuff like this. There's a lot of M256. These means that's doing the AVX2, the 256-bit operations. And so it's using masks, permutations, stores, etc. But that doesn't explain everything. It's also got a really good base case. So they're not doing an insertion sort. They are instead doing some networks. And in fact, I'm not sure which one is being called. There's a few different networks. I did see this one. It's pretty serious. So all of these source files are generated from optimal networks described in... A sorting network just means that go through every single one, make this comparison, this comparison, this comparison, a fixed number of operations, and it's going to happen really fast. Here's the network. The indices are going pretty high, 32 perhaps, yeah. So it looks like we're doing a fixed network on perhaps length 32. It's going to be tough. But let's work towards it. If we can approach this kind of efficiency, and we're still better than it on the other places like reverse and near sorted, I'm pretty happy. Let's get ourselves somewhere down here. Okay, let's find out where we are in the code. Right, this one... this one is the quicksort. So I'm doing 2 separate paths, as I said. One of them now has its own partition, splitting it into 2 bins. We can optimize for that particular case. Overall, we see it's taking perhaps 4 out of 10, 2/3, half the time. Partition 2. And it's a little bit longer than it needs to be. Okay, this can be very short and succinct. What I was trying to do here was work from right to left through the arrays, so that it was more likely to eliminate the bounds checks. You can just do that very standard little loop that looks something like this, with a swap at the end. Yeah, it's not going to be much different. Just trying stuff out. So this is a second for conditional, well, I is greater than or equal to 0. This is, one of them moving left. So it's going to do that for every single swap, once per swap. And then when it does a swap, the 2 are going to run down to find the next out of place down here. Here, more comparisons. this is the walking one of the bins, walking right to left, and similar here. I think you just have to add these up. I don't believe there's enough precision in this timing. So that's sort of 1.5 seconds. That's 1.5 seconds, which is most of the time, and then we've got another 1 second up here. We can definitely speed up the walking because that can be parallelized. Right, here's sample sort. So this one's just called partition. It's the original one. It's a higher proportion of the time compared to the insertion sorts. So we are still putting in arbitrary bins. However, I'm assuming there are 8 pivots exactly. Choosing which bin is the target for a number. So you've pulled out one value, you decide which bin to go in. You have to compare it against all the pivots, and you can do that in parallel. So it's still taking half a second, and then just choosing one of the bins, pulling out of memory. Then we've got, this one is exactly the same as what we saw in quicksort. It's walking up through one bin from left to right. That's taking a second, so that's, what, 1/6 of the time. And then we trim the bin, which is just moving our position forward. As we know, some of it has been sorted. It feels like dealing with these bins is going to be part of it, or just ensuring that we do fewer swaps, which means you're more sorted. Yeah. Today, let's work on the quicksort. We're going to work on this bit here. If we can get it going in quicksort, then I can plug it into this piece of code as well. Right, this is it. This is that code going right to left. It's a bit ugly. Let's just go make a really simple version, like more straightforward than this, where we do the regular left to right through both of them. And okay, what I want to do is, it's a for loop until we're up to the pivot. For I is less than, what? No, J is less. Come on, AI. That's better. We want the arch simmed. So we want to load a value for, no, look, walk the left forward. We're going to walk forward. The -8 is so that we don't overrun the end. So after that, we're going to have to do... I've already got I, yeah. This is what it was trying to type in before. For I is left, listen to that. Correct, we want the arch simmed. Okay, now I want to have the less than. Let's just copy that. We can do J as well. Yeah. It's the same thing. We need the right from the J to J. Oh yeah, you knew what I was about to do. Do the rights. That needs to be J++. And then we can do the swap. So it's saying we haven't walked forward too far. We have to do that check. Probably. Yes. Over here, now we've loaded 8 values at once. Normally you do it one at a time, walking through it. We want to compare all of these to the pivot, and we want, in the left bin, we want to run forward until we find something out of place, which is going to be one that is greater than the pivot value. Correct. I like how it's learning how I code now. 2 bits. Let me double check that. This one produces a mask. So if it produces, yeah, let's have a look at the simmed operations. Yeah, here we go with the mask. So things we can do with it, we can do an and an or, 2 bits, which is actually, okay, accelerated, or 2 and int 32. Whereas if we look at the int32, it's got an is0, I think. Where are you hiding? Probably alphabetic order. Yeah, this is kind of like a horizontal one. Let's double check that. Yeah, 0 returns true if all elements of x are zeros. So if we've loaded 8 things up, compared to the pivot, they're all zeros, we can skip forward by 8. So this will be accelerating 1. Is it better than doing the 2 bits? So let's just say it's like this, not these, but we want to do it as in, just call it greater than GT. If as int 32 by 8. Not 2 bits. So yeah, it's seen me doing the 2 bits before, and now it doesn't. No, not equal to 0, is 0. Not as, but 2. If it's 0, otherwise, we trailing or leading. So whatever those earliest ones are, it's going to be the exact same as the pivots. Partition 2, trailing. And then the other place we've used it, here, yes. This is in the partition where I did the trick with comparing against all pivots, and where it's obviously learnt that I'd like to do 2 bits. It's trailing, not leading. Yep, okay. So that means if it's all 8, we skip ahead 8. If it's only a subset of it, we only skip. Are we plus equal? Yes, plus equal to the number of 0 bits. So however many were greater than it is greater than when it's 1. All the ones that are not greater than. Yep. And in this case here, we don't need to check the rest of the loop. Precisely. No, that's not what I meant. Not this loop, not this for loop here. We don't have to check this loop down below. So this is where not happy with that? Oh, yep. And so we want to break to, go to, because we break to outside a block. Right, and that way, if we've gone up 8 by 8 by 8, we've hit the end, we still haven't found one, so therefore we do a walk up for the remainder. With this one, we've hit it, we've gone forward by the zeros, so we're pointing at one that's out of place already. Perfect. Now we just have to repeat this. Less, exactly. If it's 0, we go up by 8. Otherwise, we're going left to right for both of them. So yes, it's still trailing, not leading. Done right. Do a swap, continue. You realize that most of this is, see. You see? Is it going to work? I've probably missed something, so let's just test for correctness. This is in quicksort. Doesn't look good. Okay, so it's stuck. I is less than the length of left. J is left to right. We go up by 8, or we go up by some other number. So that is moving forward. I moves forward. J is less than the length of right minus 8. Oh, we've got I++. It has to be J. Anything else where I is left over? Not that I can see. Right, let's try this. It works. So let's find out how fast it was. Do the benchmark. Have a quick peek where that would sit. Yeah, that's just fractionally under the PDQ sort. So this one would have, it's a sample sort. The blue one would now be sitting up here. That's good. Getting faster than PDQ sort on all examples is what I want. see what the bottleneck is, if we can do something slightly smarter there. Ooh, insertion sort is actually taking more time than partition 2 now. Wow, that's great. Okay. Yeah, the 2 bits is slow. Greater than or equal to, I shift it into that doesn't seem to cost too much. So the alternative is I could have turned it into 2 bits every time and then done an equals 0 check. What else is slow? This one is less, no apparent reason. Break and we do the actual swap itself. You know what, this is good enough. I only have so much time, it's a bit of improvement. What I'll do, I'll add the same kind of simmed operation throughout the rest. In future videos, maybe we'll see the improvements and where it ends up, but I'll focus more on other sorts and how they match, and we'll do a bit more. Alright, so it's not an absolute victory. So the blue is the one that we just did an update for. It has improved the best case, but for smaller array sizes, it's still not better than PDQ sort, which is the yellow. Yeah, let's just add more. I will just add some more improvements, and I'll come back later when we perhaps compare some other sorting algorithms, see how close to this we can get. In particular, I think sorting out the base case is going to be room for a big win. Till next time.